Let's talk about free body diagrams, which are diagrams that show the relative magnitude and direction of forces acting upon an object. Now, we've already discussed the forces acting upon this crate, which is the object in this scenario. It is important to understand that when you're doing free body diagrams, the length of the arrow represents the relative magnitude of the force. And I'll explain what that means. Let's look at the forces on this crate again. You can see there is the force applied. That's the force of the man on the crate. There's the force of friction. That is the force of the road on the crate. There is the force of gravity. That is the force of the earth on the crate. There is force normal. That is the force of the road on the crate. Now, let's look at this scenario in which I am pulling the rope, causing the object to slide at a constant speed to the right. So let's go ahead and look at that. All right, so in that particular scenario, I am going to for sure underline this, a constant speed. That's important to keep in mind. Pause the video and see if you can identify the forces acting upon this object. We have the force of the surface onto the object. That's the upward force acting in the y direction. We have our long range force or field force, the downward force of the earth on the crate. We have the leftward force of the surface on the object. And then we have the rightward force. That would be that tension force from me pulling the object. And it is acting to the right. I want you to look at the relative lengths of these four forces. And I want you to look at them in the y direction. Notice the lengths are the same. They're opposite in direction. They cancel out. Same goes for in the x direction. Force of friction is equal in magnitude but opposite in direction to the tension force in this case. Now, here's another way you'll often do free body diagrams on exams and quizzes. So rather than drawing the arrows directly onto the object as we've done with the man in the crate, you will have a dot that represents the object. So this dot is where you will start your free body diagram. And we're going to represent each force by an arrow starting on and pointing away from the dot. So you can see how similar these are. I just want you to be aware that oftentimes on assessments, you'll be asked to draw your free body diagrams on a dot. And on the problem sets that I explained throughout this unit, I will typically use a dot and draw and label my forces from that dot, which represents the center of mass of the object, even though not all these forces are acting upon this center of mass. In fact, only one of them is acting. And that's a point that I don't even need to get into right now. Let's go ahead and look at the scenario where I was pulling the object on a rope, pulling it to the right. Well, here would be the free body diagram on this dot representing that motion. Again, recognize the direction and the length of the four forces acting upon the object. All right, so let's get some more practice here. Here, I'm pulling an object across a surface, and that surface has negligible friction. In other words, we will neglect friction. There is no friction for this scenario, which means if you draw your free body diagram onto the object, you can see here we have force normal, then equal in magnitude, opposite in direction, we have the force of gravity, and then of course the force of me pulling on the object, force of tension, but there is no leftward force to counterbalance the rightward force of tension. In other words, these forces are not balanced. Recall from previous videos in our discussion of inertia and inertial mass, and the fact that objects have this tendency to resist a change in their state of motion, in other words, an acceleration, unless acted upon by a net external force, okay? And we have that going on here. If we look at the numerator here, in the x direction, we have a force to the right, okay? And that's being divided by mass, which is scalar. That will give us a value that is non-zero for acceleration, which means this object is going to accelerate as a result. And we're going to talk about this extensively, and I have many more examples to go through. Now, on the dot method, we would simply put these three forces and represent them on the dot, as you can see here. All right, here's another scenario. I'm going to pull the rope and the object will accelerate across a rough surface. Okay, so the object accelerates across a rough surface. Go ahead, let's underline it. That's very important. Let's represent our forces: force normal, force of gravity. We have our force of friction because we are also told it is rough. So that means we do not neglect friction. So friction is present. I want you to look at my force vector. Notice that it is drawn longer than the force of friction. So there's, again, it's not balanced. All right. So that accentuates the fact that the magnitude of the tension force, which I've drawn to be greater, means that there is a greater force to the right than to the left, which means, again, when you are looking at the equation for acceleration discussed in previous videos, you will get a non-zero value. In other words, this object is going to accelerate. It is going to have a change in its state of motion. Representing these four forces, again, on the dot, you can see the rightward force of the rope onto the object has been drawn to be greater in magnitude than the leftward force of the surface on the object, which would be the force of friction. Okay, here we have a ball that is stationary on the ground. Again, feel free to pause the video and start doing these on your own. All right, free body diagram. We have the force of the surface upward on the ball. We have the downward force of the earth on the ball. That would be the force of gravity. And that is the free body diagram drawn onto the object. Using the dot method, it's the exact same. And now let's look at another scenario in which a ball rolls across the ground at a constant speed. Okay, so, all right, just going by there. Let's use the dot method. You already saw I had it labeled as it rolled on by, that there's no forces acting in the x direction. Now, a lot of students say, how is that possible? There has to be some force applied or something if it's rolling across at a constant velocity. True, something must have caused that change in its state of motion initially, but we're not worried about that whatsoever now. We just know that if it has a constant velocity, that means it's not accelerating. There's no net external force in the x direction, which means the only two forces acting on this object would be force normal and force of gravity, which are opposite in direction and equal in magnitude. Again, here, however, we're going to see a change in the state of motion. We're going to see the ball decelerate to a stop, which means that the force of friction acting in this scenario to the left is causing the object to decelerate, okay? There's no other forces, so we're not going to make any other forces up. We have two contact forces and one long-range force in this scenario to make up our three forces. How about this one, where a ball is kicked and it flies through the air? All right, so if we were to analyze this at the top of the ball's trajectory, let's go ahead and do a free body diagram. what you're going to find out is when you look at this, don't make any forces up. There's only one force for this object in projectile motion, and that would be the downward force of the earth on the object. Okay, now please remember that we're neglecting air resistance unless explicitly stated in the problem. Also, make note, this free body diagram would be the same for any position along the ball's trajectory. Now let's look at our dot here, and you can see that we only have one force. That would be the downward force of the earth on the ball. So in this video, I've given you an introduction for how to use free body diagrams to solve problems and to re-express them into mathematical relationships. And I'll see you guys in class.